Good afternoon. My name is Husban Siddiqi, and I'm Visual Systems Lead at Frazer-Nash Research Limited. This is my colleague, Silas Osborne. He's also part of the Visual Systems team. So with today's presentation, we're hoping to go through basically an overview of Frazer-Nash as a company, kind of our background, what we originally do, and then how we kind of also got into VR along the way. Along with some of the challenges and technical issues we faced and how we overcame them. So let's get started. So basically, Frazer-Nash is the primary company, and Frazer-Nash is basically oriented around powertrains and energy systems for automotive and grid applications. But we also do R&D into different areas, hopefully, some of which will get into the public domain over time. But then we also have many sister companies, courtesy of Camcorp Group. So the first and notable one is Metrocab, which will be the world's first provider of range-extended electric taxis, which we'll kind of get into a little bit later. But it's quite significant. Then we have Bristol Cars. Bristol Cars, we acquired them, and they have just celebrated their 70th anniversary with the Bristol Bullet, and we have a VR experience that is related to that. Then we have some additional companies, URT Group, who are one of the world's most foremost companies in composites and carbon fiber. They actually did a lot of contribution with regards to the Bloodhound supersonic craft, designing the cockpit as well as some of the additional materials and structures for it. Then we have EAS. They are our batteries, chemistries, as well as industrial supplier of batteries, who have supplied batteries for the Proton rocket, among other projects, as well as the Metrocab. And lastly, we have Solvam GSC. So Solvam is a ground support equipment supplier for aircraft. And essentially what you're looking at from these companies here is that Frazer-Nash provides this core technology, and URT also provides its expertise. But then we also see Bristol and Solvam as companies to deliver that technology. So we have the process for R&D. We are able to prototype, manufacture, and apply them for real-world applications. So just to continue, let's first go over the range-extended electric powertrain. What makes it unique? Well, firstly, it's a scalable, low-emission, range-extended electric powertrain. So it can be applied to a variety of vehicles, say a vehicle the size of a go-kart, or even the Metrocab, which is a four-wheel drive vehicle. But then we also have it could be targeted for trucks, buses, or even a 24-wheel monorail, which is a whole other story. But it is possible to do that with our powertrain. Then what we also have is our core technology oriented around one electric motor per wheel. This is significant because by digitally driving the wheels through the motors, it essentially means that you have a greater control than one ordinarily would. Then we've also got an internal combustion engine which powers a match generator, and that charges the battery pack, which then in turn supplies energy to the motors. So what is important about this is that the engine isn't actually running any of the drive of the vehicle, it's merely supplying energy to it. And as a result, it means that by running the engine at a constant rate, it means you are maximizing the efficiency of the engine. Then we also have our unique and proprietary digital differential. This is to act in place of a mechanical differential which would ordinarily be used, and the important thing about this is that it is actually able to use the data that is provided from all the electronic components and better improve the drive of the vehicle. Then lastly, our powertrain is ISO 26262 compliant. What this means is that we have met the latest standards in terms of functionally safety of designing our components, and along with that, it means we have a complete audit of all the work that we're doing. So we've got the Metrocab here. It meets the most stringent requirements of London Taxi, including a turning circle of 7.62 meters. And along with that, we achieve a fuel economy of 98 miles per gallon. And then we have a pure electric range of 70 kilometers with a 1 liter petrol range extender. And we are also plug-in standard with both the regular plugs that you see around in charging stations, but we also have our own plug that can be used as well. So in terms of group expertise, we do a variety of things. We've got mechanical design and packaging, thermal modeling, software development and validation, electrical and electronic design simulation, ASIC design, smart grid R&D, low volume production, safety and testing, and of course, why we're here today, virtual reality. So just to give you a quick primer, what is virtual reality? Virtual reality is essentially it's essentially making use of a technology called a head-mounted display, or an HMD, and this is placed over the user's vision. And what this basically allows is, for one, the user to spatially view and interact with objects, and along with this, it enables complete immersion. So the significance of spatial-oriented immersion means that you can actually be able to see detail that is simply not possible on a monitor, because on a monitor you can kind of look at it, but it's still two-dimensional at the end of the day. And even though you can rotate a 3D object, you still don't have a clear idea how it appears. Then along with this, you've got complete immersion, and what complete immersion implies is that essentially akin to something like headphones, where you can better get an audio experience and be able to focus your ears on the audio. That's what a VR headset does. A VR headset, it allows one to visually focus on the content that is in front of them, and they can spatially bring that towards them. And one last point that should be brought up is that it is both cost and time saving. Our start with VR was initially, our mechanical engineers had an issue that they couldn't resolve whether or not a vehicle, there was some packaging with some components, and what we did was we took those components and put them in the VR, and as a result of doing that, they were able to identify issues with packaging. The significance of this is that we were able to visualize and see something before it was created, and as a result, we saved money in terms of we didn't manufacture a bunch of components which wouldn't have packaged correctly, but we've also got time saving in terms of they were able to make the amendments, and that would later save time in terms of production. Now, in terms of the applications we've had on the show floor today, we've had the virtual mechanic, which allows you to inspect, interact, and learn about the vehicle components with relation to our taxi. And then lastly, we've got the Bristol Bullet experience. And so what this allows the user to do is personalize the Bristol car to their liking, and along with it, it enables interaction with the vehicle. And so really what we're showing here is one industry-facing application for VR, and then we have one consumer-facing experience for VR. Now I'll hand it over to Silas, who will kind of take you through the challenges and issues that we had with these developing these applications. Thank you.
Okay. Okay. So the virtual mechanic. The virtual mechanic is a digital showcase of our CAD designs and electronic displays. It is essentially a means of interacting and manipulating our technology in a virtual sandbox environment. So this is designed as an internal application and was meant to educate people about our powertrain in an immersive way. To serve the same, we wanted to be able to blow up elements of the powertrain and display each component's CAD analog, an action which we called magnify mode. In addition, most objects in the scene had to be interactable to varying degrees. So this created an issue: how to handle a very large number of different interactions and states. With any sandbox experience come challenges. Almost every object near the player needed to have a core set of interactions, and some of them additionally had to be magnified. However, each object worked in a slightly different way, and so needed a different implementation. This resulted in having to handle a large number of interactions. The number itself was not overwhelming, but was enough so that a naive implementation would be insufficient. No? No guy? Let's see. Oh, perfect. Okay, perfect. So, issues and solutions. One of our first playtesters tried to throw our battery box, which resulted in it being unsatisfyingly dropped. So we added enough actions so that the most common things people would try would be represented in the game. Now, in this way, we attempted to replicate reality. The problem is that people have certain expectations about what happens when you throw an object. And if the expected response doesn't occur, then it creates a disconnect, which can break immersion with the user. Okay. So pick up, hold, drop, and throw actions were required. Our first attempt to build an interaction system tried to put all the actions and fit them into collision states on the controller. When the controller touched an object, it triggered a begin event. When it was held on an object, it triggered a stay event. And if you took the controller off the object, it triggered an exit event. So the pickup corresponded to it being an event. Hold was just the object being held throughout the stay event. And drop, throw, and snap had to be negotiated in the exit event. So dropping and throwing an object was relatively simple. We could either rely wholly on the physics system and then apply velocity and angular velocity of the controller to the object that was being thrown, or perhaps set a cutoff point that anything below a certain threshold would be a drop, and anything above would be a throw. In addition, we had to check if the object was in proximity to its snapping point. The powertrain components all needed to fit together in a very certain way, so we made template positions for them to fit exactly together. So if the object was within snapping distance, it would obviously not gain any velocity and would simply move to its templated position. Yeah, as you can see in these pictures. Okay, so just to clarify, inspect mode is the normal mode where you can pick up objects, and magnify mode is where you blow up one object and can see it in CAD. So in the early stages, even switching between magnify and inspect mode changed what pickup and drop did. There were different rules for the CAD objects. They were physically heavier, and some were not throwable because we didn't want people to lose the items, which all proved to be rather futile because you can increase the mass of objects, but the forces that the controller can exert on the objects largely stay the same, which is good and realistic. However, people really want to throw improbably heavy objects, and if you have a really large mass, then they can't. So ultimately, we kind of had to abandon any attempt at realism in favor of player choice. Eventually, though, we went for feature parity between inspect and magnify mode, and in a way, we designed out some of that complexity. So the solution to this was object-defined behaviors. So obviously, some objects had different things they needed to do on pickup, and even before pickup. So we couldn't get all this information right then, and so we had to convey it before the begin event. So certain actions like disabling highlighting on touch would not work because information would be passed after the begin event had been triggered. Ultimately, we sort of rethought this and offloaded all the interaction code to the objects themselves. So they kept track of their own actions and whether they were supposed to be in magnify mode or inspect, and their own implementations of pickup, hold, and drop. This meant that the controller code could be vastly simplified. Now the controller just had the three events: begin, hold, and exit. In each event, the object's interaction script just gets a reference to the controller, which tells it which phase it's in. The interaction script then just executes the code for each phase. This resulted in a vastly more flexible solution that could easily be tuned to fit a wide variety of objects. Okay, so Bristol Configurator. Hopefully this will be a little bit less technical. The Bristol Configurator is a virtual car configurator with a full-size model of the Bristol Bullet. As you can see there, it contains openable doors, a configuration menu which alters the paint and trim in real time, and a teleportation system for traversing the space. So unlike the virtual mechanic, the Bristol Configurator was designed for the explicit purpose of serving a customer need. The concept was for the application to exist in a showroom environment where the customer could put a Vive on and see configuration changes in real time. Then save out their selections for the salesperson to view later. So this is quite focused experience, therefore limited in scope compared to the virtual mechanic. Okay, so our first issue was how to represent a virtual palette in world space. We wanted to display multiple configuration options. We had colors for the paint, colors for leather, colors for the body, and a variety of different trim options for like the dashboard and clock. Though we knew this would require multiple panels of information, we also knew that we could probably not display all that information at the same time. Therefore, there needed to be some way of switching between different groups of selections. So, right. Okay. Initial thoughts centered around a virtual book, possibly, a panel in world space, or a handheld tablet. We initially thought of a virtual book of color swatches. That's similar to how people might select, say, colors for a car in real life. This option was appealing, and we thought that the user might be able to pick it up, say, from a table and take it around with them. This didn't work so well in practice because it became clear that people wanted to be able to bring up the configuration menu at any time. So, what we thought was a feature ended up being more of a limitation. Another thought we had was a handheld tablet that could be swiped around. This is actually quite close to what we ended up choosing in the end, although the actual version doesn't look like a real tablet. Okay, the last thing we thought of was simply having the information in world space as a panel. So some sort of diegetic UI, i.e. an electronic display like a TV, possibly, or kind of life-size tablet which you could interact with. But that had the same issue as the virtual book, in that the user would have to teleport back to the panel's location in order to change options, which is not quick or even intuitive. So it was pretty difficult to conceptualize which would be easiest for users to grasp. It's quite difficult, to consider how people would want to interact with the information without testing it. Over testing, though, it emerged that people essentially wanted to bring up the menu wherever they are. That's part of the freedom of being able to teleport or walk all around the vehicle, and therefore we decided on making the panel come to you. So the solution ended up being having swiping and tapping a touchpad to cycle between information panels. The configuration menu can be brought up at any time, and we coded swiping to switch between the different configuration panels, as we thought it would be a more recognizable means of interfacing with the panel. We're used to swiping from our phones and tablets, so I thought it would be intuitive. However, others found that a positive action, such as pressing the button on either the left or right side, to be superior, and which did eliminate some errors with the panel moving unexpectedly if the user brushed over them. Now, once you've selected a panel, such as body paint, say, then options are then changed by using a laser pointer. The same pointer you use to teleport, when put over the configuration menu, can select colors and trim. You simply pull the trigger to confirm the selection. So the result is then reflected immediately on the car for you to see. So those are just two examples of some challenges we faced, and with solutions which hopefully can be applicable in like a wider way. Right. Thank you.
Okay. All right. Okay, so just some takeaways really from this presentation. Firstly, think about and design your interactions as early as possible for VR. Because VR is spatial, it means that you have to rethink of the way that people interact with them. Secondly, also try to think about the convenience side of VR for user interfaces. It's almost like in real life, if I didn't have to walk and I could just move over there with just thinking about it, we would do that. So it's really about thinking about how VR can almost be like a reality plus, making things more convenient for people to bring up. And then lastly, leverage VR's complete immersion. The fact that it's spatial, the fact that the user's vision is focused on the 3D experience in front of them, it definitely adds something greater than usually a display or a monitor can. Thank you very much for listening to our presentation. If you're interested, drop me an email or pop by our booth. And if there are any questions, feel free to ask. Thank you so much for your time.
Okay, thank you.
Thank you.